Welcome to Study Unit 5 on restricted data structures. Now, restricted data structures is really an extension of arrays and linked lists, those structures we've done in Study Unit 3 and 4. We will use also those data structures to implement stacks and queues. Stacks and queues, the work has very little new information and you can relax a bit. You will learn a lot of new things, but it won't extend you that much, not nearly as much as linked lists extended your knowledge. Stacks and queues are known as restricted structures. Now, a restricted structure means it's restricted in terms of access. Now, what do I mean? I mean that you cannot manipulate the stack and the queue the same as an array or linked list. Technically, you can add items in the middle of those lists at the end. You can delete items in the middle of the list, delete items at the end. But not the case with stacks and queues. It is restricted. So you can only access these structures according to some rules, which we will do later on. Now we are going to focus on two, stacks and queues. Stacks are used in computer science all the time, inside your computer. For example, it is a stack that manages the parameter passing. You might know that there's a website called Stack Overflow, or where people solve programming problems. You can post any programming problem on Stack Overflow and some people will give you advice there. Now, why is it called Stack Overflow? It's because all over time, when a programmer gets an error he cannot solve, it's typically a Stack Overflow error. And it was such a common error. You have it in today, it's almost like your null pointer exception. You know, when you do your practicals and you get a null pointer exception, you're kind of, don't know what's this or where it comes from. Now, in the old days, it was Stack Overflow errors. And that is why that website decided to call themselves Stack Overflow. So stack is used all over computers. And after this study unit, you will know exactly why and how to use it. The most common function of a stack you are aware of is the undo function in the Microsoft projects or packages. You know that you can keep on undoing and undoing and undoing and redo, but it is all in the same order. From your lastmost action is the one that is undo or undid first. Where do we use queues? Queues are always used in scheduling algorithm. Normally it's on the basis first come, first serve. So every time every time you have the situation where the task that's first received must be first accomplished or finished, it is called first come, first serve basis, and that's when you use a queue. Okay, let's talk more about general lists before we go to the restricted list. So for unrestricted lists, if we have an array implementation, you know an array is drawn like that with all the items next to it, I can say data 5. That means I have direct access to the fifth element in the array. You never thought that is so special, hey? But in a queue or a stack you don't have that. For linked list, I can also access one specific element. It's harder. I have easy access to the beginning and the end, you should know now, because of head and tail. But even in the middle, I can change the value. It's just a bit harder. I need to traverse the list. Now, this is not the case with stacks and queues. We will first focus our attention on stacks. Now, it helps if you have a mental model of stack. A stack is a LIFO structure. LIFO. Last in, first out. Think about it. Last in, first out. I spoke about those undo items on Word. I want you to make a mental model of a stack of plates. Dinner plates like this picture here. Have you seen it in a restaurant or perhaps on television of a restaurant kitchen. Some people washes the dishes. They will add the stack, a clean dish at the top of the stack. We call this the top. And other people in the restaurant will take a dish from the top. So you will put something on the top and you will take it from the top. Now the two operations have very cool names. To add something on the stack is called push, and to take something from the stack is called pop. Now it originated really from plates. You're not old enough to know this, and money is not spent on such nice things anymore. But when I grew up in smart restaurants, the stack of plates were kind of sunken in the table. And underneath the table was a spring, and there was a bracket that keeps the plates at the same height. So you would pop yourself a plate. You will take the plate, and then the other plates will push up after you have done it. And if somebody wants to add another plate, he needs to push down on that stack to put the plate on the stack. Now today in a refrigerator in a shop, like in next to a fueling station, you get those refrigerators where you open up and then you can take a can of cool drink there, and then the one after that is sort of pushed, or your can pops out. So that is the idea here, that you take the can and it pops out. I'm trying to help you to memorize this, so stay with me. Now the refrigerators has a different property. They can be loaded from the back. But let's say they cannot be loaded from the back. Can you then see that the person loading them with stock will have to push everyone down or push everyone back in the spring? So get a mental image of either a pile of plates or cokes in a refrigerator or something that will help you to understand that push is adding things to the stack and pop is taking one. But the key idea is that both operators are happening at the same end. I want you to form a mental model of the stack of plates. So in the exam, when you see stack, I want you to focus on a stack of plates, because then you will remember that push and pop are the two words. Push to put something on the stack, pop to remove it, and also it all happens at the same place, the top of the stack. Okay, let's visit queues. So you know now, a stack is restricted. It can only have access at one side. Queue is less restrictive. It's called a FIFO. Do you know FIFO? First in, first out. First in, first out. So, what does it mean? It means that you are waiting for a bus. And the person arriving first will be in the front of the queue. Other people will arrive at the rear of the queue. And the person that's first in the queue will first get on the bus. First in, first out. The two terms you need to know is NQ and DQ. It's sometimes spelled differently. Some textbooks, I think they take sort of a shortcut and to remove that last UE. But I'm so satisfied that I can spell Q that I keep them there. So NQ, add something to the queue, remove something from a queue with DQ. But the key factor, it is done at different ends of the list. So it's still restricted. You can only add at one end and delete at another end. Okay, now for the implementation. The implementation we are going to do with both arrays and linked lists. So you can have now in your mind that you are going to study for stack, you are going to study push for array, push for linked list. For queue, you are going to study in queue for an array, in queue for a linked list. So it's actually 8 methods, so 4 methods, 2 for stack and 2 for queue, both on arrays and linked lists, which you have to know for the exam. But I'm sure if I ask you in the exam now, without even looking at the next slide, you will all be able to do it just from your knowledge up to now. Okay, so both these implementations, the stack and the array and the linked list and the stack and the queue, has advantages and disadvantages. And we have to figure out how we are going to do, at what end of the linked list are we going to manage the stack, the head end or the tail end. Luckily, we have study unit 2, and you can make an informed decision. So in this study unit, we are going to talk a lot about asymptotic analysis, order in analysis. So we will first do the linked list implementation, since linked lists are now fresh in your memory, and then we will do the array implementation. So we are going to start with a stack and then follow with a queue. So now that you know what a stack is, you know what a queue is, and you know that we are going to implement both of those structures, both using arrays and linked lists, we are ready to start with the first one of the 4. That is a stack as a linked list. Now you know from our stack of plates that we are going to restrict the axis. We are going to have only new plates at the top of the stack, and we are going to remove items or plates at the top of the stack. So, but we have to make this decision. Which is easier and why? Should we do it on the head side or the tail side? Now I promised you that we are going to do this with the work of study unit 2. But let's think about it. Let's focus on the head side. If we think about push, it means that that element was new now. And you know that if I push an element, a node, into a linked list, I have to change the head, and there's a special case that it might be an empty list, and then I have to change the tail. My question to you is, order how many is that? Let's make it easier. Is it order 1 or order n? When will it be order n? It will be order n when I have to traverse the entire list. Did I traverse the entire list to add something to the head of the linked list? The answer is no. Therefore, this is an order 1 operation, because I did not traverse the list. If I add something to the tail side of the list, think about it. So I added, let's say, that element in my linked list. Do I need to traverse the entire list? Now you have to think back about study unit 4. What is it called? Append. You studied append very hard. Do you need to traverse the entire list when you append? No, you are right. You only need to change the tail, and in the special case the head. Let's think about pop. Pop means remove the element. I'm going to remove that element. My question to you is, order what? Do I need to traverse the entire list to do this? No, I can simply remove the head. But if I have to remove the tail, If I go directly there and from talent remove it, there's something else I have to do. I have to take this element's address back to tail. Do you remember the new tail? And how do I know where the new tail is? You are right, I have to traverse the entire list with a pointer and the previous pointer. To delete that last element, I need to remember the previous elements, so I'm going to traverse the entire list with that order in. A push and pop happens at the same end of the list. Now you should ask yourself, which is better, the head or the tail side? What do you think, and why? I think that the head side is better, because both the push and the pop operators can be done in order 1. Where if you go for the tail side, this pop here will take order N. It's much quicker to pop at the head side, easier programming as well. So we are going to pop at the and push at the head side. Now can you remember that if we add something to the beginning of the list, you have done it. Can you still remember what it's called? I think you can. Prepend. Can you remember how to remove an element at the beginning of the list? I think our class do have a method called remove first, but we are not going to use it. How do we remove something at the beginning of the list? Actually, there are 2 ways. You can either say head is head.next, or you can do this, you can call your delete method for your head. This is an oversimplification, because this head is an address and delete works with an element. So you should actually call head.data. But the idea is you just delete the head. We will get to the nitty-gritty linked list just in a moment's time. And that moment is now. So let's have a look at this code. It's a class called stack as my linked list. So previously you had 2 classes. You had the my linked list, and then you had a test my linked list. Now you have 3 classes. You have a my linked list, and then a stack as a my linked list using this linked list, and then you will have a test class as well. So that's almost the most difficult thing to understand, is that you have a stack as my linked list that actually uses this class my linked list. Okay, so you create your own class, stack as my linked list, and in it has one instance variable which we call the stack. Okay, but that stack, what data type is it? It's a my linked list, the class we developed in the earlier study units. And the constructor, what does it do? It creates a new stack. Now look at push. Let's go back. Did we say we are going to prepend? Yes. Push receives the new element, but note the type. Remember, the user only works with e's or integers or whatever. It never considers addresses. Never consider address from the test program. So here we prepend the data part, the element part, to the list we call the stack. Do you understand push? Pop is a little bit more complicated because we want to make sure that the list is not empty. So we are going to use the method get first, or get head in some implementations in other textbooks. So we will get head, assign it to temp, that temp, is of type E, because get first only gets the data part, the element part of that first node. And then we will check if it's null. When will it be null? Get first brings back a null typically when the stack is empty. And if it's not empty, temp is not null, and now I can delete temp. So temp contains the data element, not the entire node, the data element of the head, and I can simply set that to delete. Remember, delete works with an E type. It's only the data element that is sent over as a parameter. Okay, so I could have said head.element. I could have also said head.element, because that's exactly what get first returns. Go to the address, so which is stored in head, go to that address and find the element there. Now, when all these booleans is done, and temp can be known, it all has to do with error checking. Delete will not in this case return a false, but it's good to check whenever you use a method to handle its return value. Why would I say it should not return a false? Because it will return a false only if you know the code of delete when the element is not in the list. But this is per definition in the list. This temp is, we first go to the list and find the first element. So that element is per definition in the list. So this is done, it will seldom be activated. It cannot really be activated because then there's a bigger problem in your list. It means the first element is not in the list, and that is not that possible. But in any case, we try to handle the return values in always. Okay, that is pop. Now stop and stare. See if you understand it. Which line don't you understand? Which aspect do you do not understand? I think the most important thing is to understand that get first returns the data element, and delete can be used then because delete works with data elements. Okay, let's quickly have a look at the test program. Move me out of the way. I'm afraid those plates are going to fall on me. Okay, interesting is that if you look, let's look at this program from inside out. It's a lot of pushes, push, 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 pop. Another pop. But here we create the stack. My stack is a new linked list, stack as linked list. Do you understand now why I said you have three classes? You have a test class, this test, my stack as linked list, which uses stack as my linked list. The driver is not using the my linked list class. This stack as my linked list, if we go back to the previous slide, is using the my linked list class for the stack itself. And we are not using the methods in the my linked list class here. We are using actually the methods of the stack as my linked list class. So you only have push and pop. And let's look at the output. Our idea is to demonstrate the stack. The stack, remember, we are pushing from the top and we are popping from the top. So we add a 3 and then we add more. So there's a 3 at the bottom, then a 2 on top of it, then a 9 and a 5 at the top. And now we are popping 1, and to pop 1 will return the 5. If we pop another one, it will return the 9. When we pop something, it is deleted, it's removed, that plate is gone. And when we pop another one, that 9 is popped, the 2 is popped, the 3 is popped, and now the last one is like the person in the restaurant and said, "There's no plates to pop because of the empty list." So you can work through this code. It's all kind of easy. It's just one little idea is that when we use pop, we convert it to an integer, to top, and because it returns an E, and then we check if it's null, because pop has a return value. But if you go back to the code, it will be easy. Do you have to convert it? You can test the code. I'm not sure. Sometimes I think the code gives an error, sometimes not. I prefer to convert it all the time. Okay, let's take a break before we do the queues as linked lists. Back to stacks and queues. You know you can do an array. You know they are restricted structures. You can implement what does that mean? You can only access it at the ends of these lists. They are different. A stack is a LIFO, last in first out. A queue is a FIFO. You know that you can do both of these with linked list and with arrays. In the previous session we did all the linked list stuff, and now we are going to do all the array stuff. I repeated the original slides. I reminded you that you can have direct access in an array but not in a stack and queue. You can even have sort of direct access in a linked list by traversing it, but not in a stack or queue. We said stacks or plates, and we have a top where we are going to add and remove things with push and pop, do you remember? And we said queues are like getting on the bus, and it is going to be one end of the queue will be served, we call it the queue, taken off, and while people are arriving, called in queue. They are getting on the bus, but the main thing is on different ends of the list, whereas if I go back to a stack, it's on the same end of the list. If I'm going too fast, go and listen to the video of session 1. Okay, we did the linked list implementation. Now we are going to go through the same effort with the array implementation. And it's easy because you know now that you have a lot of work in study unit 3 you can rely on. But we are going to do two options. We are going to use study unit 3 to do the array list, my array list, but it's not optimal. It's really not optimal because part of that array list shifts to the elements. We will also look at the standard Java array. Now I'm taking you back to last semester to work with a standard array. So we will first do the my array list class. It's quick and easy, and then we will have a very, very, very interesting time discussing the standard array. So if your mind should be in arrays, adjacent elements. So we are first going to do the stack, and we are first going to decide which end. Are we going to do it in the front or the rear? It's influenced by the fact that we are using my array list. Because you will remember, my array list is so fancy. Whenever we add or remove something, it shifts the elements. Things to remember that. Quickly go to the code, pause, and go to the code of my array list and have a look at the add and the delete. It shifts the elements. I'm waiting for you. Are you back? Did you see how it shifts the elements whenever you delete something? So this To delete something at the end means all the elements will be shifted. Do you agree that that is order in? If I add something in the beginning, all the elements are shifted. You see in the code. So that's also order in. Remember order in every time I run through the entire list. Now if I add something at the rear, that's order 1, because there's nothing to shift. If I remove something from the rear, it's order 1 because there's nothing to shift. We are working with a stack. Can you still remember that all the operations happen at one end? So we should decide whether we are going to go with the front or the rear. Which one are we doing? Yes, you know, the rear. We are getting there. Why? Because the rear is order 1 and not order in. But so we are going to add an element to the end of the list, and we are going to remove an element from the beginning of the list. Let's revisit our diagram. An array has an index. What are we trying to do at the end of the list and the end of the list? How do we know where's the end of the list? Yeah, we have a size variable, and that size variable gives technically it gives the number of items in the list, but it sort of gives the index of the first open position. Think about it. It's logical, but it's very clever. Size tells us there are 7, but since it is numbered from 0 to 6, the 7 itself you can view as the index of the first open position. Do you agree? The value of size is the index of the first open position. And size minus 1. Size is 7 minus 1 is 6, gives you the last filled position. You have to understand this before we continue. If you don't, rewind, listen again, or just think about it. That size, although it's just a number indicating the number of filled elements, actually has this very cool property that it gives you the index of the first empty element, and size minus 1 the index of the filled one. So it's easy. Did you see when you went back to that array list class, my array list class, how to remove items? Did you see we give it the index? Did you also see when you went back and checked the add, that we add with an index? So if we go to push, oh, there's something new. Why on earth are we doing check space? You will see check space is a new method I added to the array list class. You see, it just compares really with mapped elements. Yes, the array can be full. I cannot just end up adding stuff to the array. The array can be full. And you have to check the array. You would have seen in the array if you went back. You can pause me again now to go and check. Did you see that mapped elements? Check space. Just find out if there's space in that array. So the same with push. It checks if there's space, and then what should be the index? Remember, add has two parameters: a new element, which comes from the parameter, and the index. And what should be the index? The index of the first open element is the size, so I get size for that. This is explained on the previous slide if you are not listening. Okay, to remove it, I also have to give an index, and I get size minus 1. Why get size minus 1? Because the size is 7 and the last one is that 6. Get size minus 1. But I have to check if get size is larger than 0, 1. I cannot pop a stack when that stack has no elements in it. I think this is easy. Do you think it's easy? The only thing you have to understand is here on the previous slide, that the size is really the first open element. Okay? To do we test it now. It's so funny. Push, 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 pop, push, push. It's exactly the same as the previous one, except we are not using stack as my linked list, but as my array list. It's only that line that differs from the previous session, because now the stack is an array and no longer a linked list. But the user doesn't know a thing. He keeps on using push and pop identical for whether it's array or linked list. Go and test, go and look up the code on your Fundi, and then you come back and you check the code here. Let's get me out of this way. Okay, now we are moving to queues. Think about the bus. We can do the myArray list class like we just did for the stack, but for the shifting around, it's not a good idea. We might want to use the standard array, but that is much fun. You will see. It's very interesting. Okay, if the bus is hitting me and get out of the way of the bus, we have to make the same decision. Are we going to go for the front or the rear? We know this one is order in. We know this one is order 1. We know this one is order 1. We know this one is order in. If I'm too quick, go back. Why hit order in? Because I have to shift all the elements. Whether I'm removing, then actually my arrow is the wrong way around. I'm shifting everything towards the gap. When I'm adding something, I'm shifting everything on back. But that's not a standard array, and that's something we built into my array list to make it fancy. If I remove something from the rear, there's nothing to shift. If I add something to the rear, there's nothing to shift. So that's why they are ordering. But for queue, I have to do this across selection because it's done on different sizes. The queue works at the front of the queue and queue at the back of the queue. So which one do I have to take? It really doesn't matter. It really doesn't matter if I do those two or if I do those two. I chose those two. Why? I think because I already had a DQ. No, I had an InQ at the back from the stack. But it would have been in any case, I would have had a DQ at the back if I chose the other two. So it really doesn't matter. So if I InQ add an element to the rear, so you know that size is the first open position, and if I want to remove it, I can simply remove it at position 0. Let's have a look at the code. So that's easy. In Q, I add something at the end, just as I did with the push. DQ, I remove it at the beginning. Check the special case, is that stack not empty, and that's it. Why am I not satisfied? I'm not satisfied because of this things ordering. And if I did not battle with this myArray class, if I did a normal array, it would have not been an issue. Now I want to show you how to do it with a normal array. But I can't if you do not understand all of this, so take a break, re-watch this. Make sure you understand the shifting. I think you have to go back to the myArray list class before you come back to see how it is done with a normal array. Now for the fun. We are going to do it with a normal Java array. But I want you to understand we are using queues. So I should have a bus picture there. Let's call it no, I want you to understand why we are doing it. This study unit 3, we created actually a wrapper class for the array. So we added a small array into a big array. And we want to show that it's possible. We wanted to do it with generics. We wanted to create a generic array. And we kind of showed you that you can say you have it improved with very much emphasis on the double quotation marks, because it's a bit sarcastic today version. And sometimes we want a lower level of access. We want to access that array directly. So we can either put some get and set methods in that class, but I don't want to confuse you that much. Or we can go for a separate Java array. We can forget about study unit 3's existence for a moment and just do it with an array. We can even do it with an array of primitive integers, just so that you can understand the idea. But that's what we are going to do. So we are going to go for something that's order 1 instead of order n. It's lots of fun. Okay, let's move on now. Here. We are going to have a simple array of 5 elements. So we can even do small integer. Then we have 2 variables, one called the rear and one front, almost like pointers in the list, but not pointers in the list, just indexes, index spaces. Okay, both 0. If we include 2, now you should be careful, but listen carefully, and it's printed in the red block. Go to rear, the old rear, see it is 0, go to 0, add the position, add the value, and increment rear, then increment. Enqueue stores a new element in data rear and increments rear. Are you with me? Let's do another one. Enqueue 12. It will go to the old value of rear, which is 1. It will store the element there, and it will increment rear. Do you get it? Okay, go to the old value of rear, which is 2. Go to position 2, enqueue 17 there, and increment rear. Now it's 3. Oh, and what does dequeue do? Dequeue falls to the front. Dequeue retrieves the element at data front and then increments front. So it goes to front, which is 0. It dequeues that and it increments. Now front is 1. If I dequeue another one, it goes to the old value. It was 1. Bang. Strike through, remove that 12, return it, and but also increment it. But you are not allowed to go to the next slide if you do not understand this. So pause now. Okay, so you understand that. Let's move to the bottom here. If I continue with this and I enqueue 8 and I enqueue 6, the rear was 3, now it's 5, which is the side. It can look like this. Do you agree? The 2 and the 12 was removed with dequeue, and I enqueued. I never dequeued the 17 on the previous slide, and I enqueued the 8 and 6. So my array kind of feels full because, hold on, you know it's full because rear is equal to side. Wow, it's full. It's full, can't be used. But is it? I think there's space. I think there's a space and there's a space. And even worst case scenario, there could have been more space. And then, we can't say this is full, can you? But if we do some mental gymnastics. And it's only mentally, it's nothing physically. It's only a mental, it's a conceptual idea. If we say, let's link the ends, okay? Let's link the ends. Let's just fix this again. Okay, I'm back from destroying the video. So let's link the ends so that we have what we call a circular cube implementation. Have a look if you can see those, if you can connect these two diagrams. Can you? Yes, I did a bit of PowerPoint magic. There is position 0, position 1, 2, 3 and 4. They sort of created a conceptual idea of a circular cube. And now I can say the cube, I need rear. I can say the moment rear must be want to go to 5, I should actually make it just 0. I can say if rear is 5, make it 0. Because then rear is not pointing at this and falling out of bounds. It just moves to the beginning. And front will be here, front. Rear there. One can only understand this if you apply bum to chair, pencil in hand, and NQTQ all the time until you see how it works. The question is when it's a Q for. One can say some clever textbooks say if rear is overtaken front. Or some other implementations like the one we are checking out is simply adding the elements with a different variable, and that must be less than size. Let's have a look here some more. Let's just find a space for myself there. I will look on from the top there. Okay, so we have to check if rear is size. So if rear, remember we increment rear. So we add something at the rear and then we increment. Here it is. We add it to rear and then we increment. So just after incrementing, if we check if it's size, we set it back to 0. And this is what happened here. I checked it was 4 and then I set it to 0 and I stored it and I incremented. Now it's 1 again. So if I make it a 5, instead of making it 5, I make it a 0. So you can do this, you can say if rear is equal to size, rear is 0. But a cool way of doing it is with this mod operator. You divide rear by the number of items, but you only take the remainder. This mod operator is something that's very useful. Perhaps you should know this. Perhaps this is a tip for assignment or exam paper or something. What does it do? It divides 5 by 5 and it takes the remainder of it. But our question still stands, when is this cube full? And the answer is when the number of filled elements are equal to the size. Here's some code. I hate to say you don't have to know this for the exam, but that's only because you don't have time. You only have 80 hours to spend at this module, and most people study it. And, that's terrible. We create a queue of small ends, primitive data type, and we have a lot of variables here, front, rear, number of nodes, and size. We have a constructor where we say the size is 100. I had just 5 now. This is a big queue, but I'm not going to draw that in PowerPoint circle, don't even go there. The number of nodes are 0 in the constructor because none are filled. From rear is 0 because nothing is filled, and it's an array, so we have to say the size of that array. There are 2 constructors. The one works with any size, no size, default of 100, default constructor. This one tells us this size, and that one I will draw if n is 5. That's what I've done. In Q, note they can't spell Q. Remember I told you somebody does this. Okay? In Q. What does in Q do? In Q, now we have to go back. In Q stores new element at data rear and increments rear. It stores a new element at the data rear and it increments it. There it increments it. Rear equals. Oof, yes, so they've done it all in one go, which makes it so hard to understand, but that's why I use this borrowed textbook so that I can teach you so much more. Rear equals first increment it and then mod it with the size. So first increment it, then mod it with the size. That is new value of rear. So if rear was 0 at the beginning, it will now be 1 mod size, means divide 1 by 5, that is 0, remainder 1, and so the mod is still 1. If rear was, let's say 4, increment it, now it's 5, 5 mod 5, means 5 divided by 5 and give the remainder, and that would be 0 if size was 5. Okay, I can see this fancy mod replaces an if, but it's only the if that replaces, nothing much fancy, but it's so cute to do it with a mod instead of an if. It's a nice application of the mod idea. The same with DQ. Now we look at the front. There's a bit of gymnastics here because they change front. So they first store front so that they can return the correct variables. Let's go back. When you DQ something, there's not a DQ, there's not a DQ. Let's go here. Do it with DQ. In a DQ, retrieves the element of front and then increment front. So because you first want to retrieve the element, you could have stored it in a temporary variable and return that later, or you can store the place where you want it in a temporary variable, and that's what they've done. They stored the place where they want to delete it in a temporary variable. See, this front location is actually the front, and that is what they want to do because they are going to change the value of front with the mod. Now, if you really go and do this, to do the toString is actually weird. You want to do it for every element, so from 1 until smaller number of nodes. That's the number of elements. But look where you start. You start at the front, and then you have 2 variables, C for the counter and I for the position. So you print data I, but data I starts at front. And you do the same trick here to make sure that when you go over the end of the list, you actually start again. So this mod replaces a lot of ifs. To me, this is way cool. And if you look at all these, this is order n, order 1. This is order 1 because you have this direct access. You don't access the entire queue, you do not shift the entire queue or the entire array. So why are we doing all this? To show you that the my array list class with the shifting and the delete and the insert creates order n methods. But by using a straight array, you have order 1. Now, could you have done it with the myArray list class? Yes, for sure. You could have added more methods to that class to have more direct access, like change the data at that specific index. So it's not that we cannot do it. It's just that we had to add so much functionality to the list, and I did not want to create more confusion when explaining that list orders work. So it's easier to understand it with a primitive array. So that's it for stacks and queues. Let's see if you are completing, if you can complete the study unit. Do you know what's the difference between a stack and a queue? Do you know that you can implement them with a linked list? Do you know which end of the linked list will the stack handle, which end of the linked list will be handled with a queue, which end to use for what in Q and DQ? Do you know why that's the case? Do you know how to do it with arrays? The stack is easier using the myArray list class. Do you know why I want to throw a myArray list class away now? Yes, it's order n, and I'm interested in order 1. Do you see that order n matters? Not if there are 5, but if there are 5,000, then it really matters. I think you will enjoy your assignment. It's an application using stacks. Okay, enjoy. We are taking a break now, and you can do your assignment, and we will continue in a week or so with study unit 6.